Hi everyone, thanks for watching. So yeah, this is joint work with Ron Raz, and let's just dive right in. So the sort of main mathematical object that we're talking about in this work is a multiplayer game. And so what this is it's an interaction that involves k players, P1 through Pk, and the referee. And what happens in this interaction is that the referee samples some queries from a set Q. So it's a tuple Q1 through Qk. And it sends each player a corresponding Q. So we think of but after all of this, the referee will just say that the players have collectively either won the game or they've lost the game. The probability that the players can win the game if they play optimally. Choice of functions and what's well, this is called the value of the game. QIP is what's the probability that the players can win the game if they're quantum. So if they start with some entangled state and they do their quantum whatever. And so this is called the entangled value of the game. A very simple way of testing that the world is actually quantum. So it turns out that there are a lot of multiplayer games. Quantum strategies can play the game perfectly. They win with probability 1, but classical strategies can be somewhat worse. It's a really simple test. It's a probabilistic test with some errors but it gives a way to test that players are actually behaving according to the laws of quantum mechanics. Because if they were limited to being classical, then they would have some probability of failing to win the game. Probability of, or the entangled value and the classical value is some constant. And you can ask how to construct a test with a larger gap, or like get the classical value to be arbitrarily close to 0. So this is called gap amplification. And there are several common approaches that you might try. So the first is called sequential repetition. It's kind of the most simple approach. And it's just to play the game n times in a row, where n is large. So if you started with a game where the entangled or quantum value is 1, then you'll still be able to win the sequentially repeated game with probability 1 because you just use the whatever quantum strategy you had and you use that n times. Similarly, the classical value kind of behaves as you'd expect when you repeat sequentially. If you started with some classical value v, where v is less than 1, then when you repeat n times, the classical value becomes v to the n. So it approaches 1 exponentially quickly. The main drawback of sequential repetition is that you're playing you and the players if you're the referee. And this can be detrimental in some settings. So an alternative that you might try is something called parallel repetition, where instead of having n rounds, you just do the game n times in parallel. So you just have one round where you send n copies of independently sampled questions to the players, and the players send back all of their n answers. And again, it's not hard to see that if the quantum value is 1 to start with, it stays 1. And you might expect that the classical value exhibits exponential decay, just like in the sequential repetition case. But unfortunately, this is not quite the case. So it turns out that parallel repetition is very subtle. It's non-trivial. There's all sorts of intuition-defying counterexamples. And in general, it's not so well understood. And I should mention one other approach to gap amplification, which is called anchoring, which essentially involves in this talk, we're going to just focus on parallel repetition as a mathematical question. All right, so what's known about parallel repetition? Well, first let's start with what's believed about parallel repetition. So it's, I think, broadly conjectured that parallel repetition should cause an exponential decay in the proven for some games, but not all games. And notably, it's been proven for all two-player games. The best general bound for arbitrary numbers of players is extremely, extremely weak. If you repeat it n times, the value goes down like 1 over the inverse Ackermann function. So it's incredibly, incredibly slow. And there actually are simple natural games for which we don't know how to prove any better bound. And in a work by Dinur et al., they speculated that there's a specific simple game called the GHZ game, which I'll describe next, which captures the general difficulty of proving parallel repetition bounds. And so that's going to be the focus of this work. So just looking at this one particular game, which is very simple, and trying to prove that when you repeat it in parallel, that the value goes down quickly. So what is this game? The GHZ game, it's a 3-player game. And all the queries or questions and answers are over the finite field F2. So how do we specify the game? So first is a query distribution. So what the referee samples is the players get queries Q1, Q2, and Q3. They're just uniformly random, subject to having even parity. And the players have to respond such that the parity of their answers is the, oh, sorry, this should be the or, not the and. There's a typo right here. This should be an or instead of an and. It's not too important, but this game has a property that the classical value is this 3/4, less than 1, and the entangled value is exactly 1. And so what we prove in this work is that when you repeat this game n times in parallel, the value decays polynomially quickly. And of course, what we hope is that the value decays exponentially quickly. But if you compare to where we started with this inverse Ackermann bound, we sort of only have one more exponential improvement. We're only one exponential improvement away from optimal. Okay. So I need to give a little bit of background on how we sort of go about proving parallel repetition bounds. And there's sort of like a standard strategy. It's very, very high level and generic. But so we start by considering this parallel repeated game. And it's actually pretty easy to just say, if you look at any particular coordinate, just take your favorite. So the first coordinate, when I say coordinate, I mean repetition. So you have n different repetitions. And in each one of these repetitions, the probability that you win in that repetition is bounded away from 1. That's not so hard. But that's where we start. Then after we've established that, we want to say that conditioned on winning in this first coordinate that we specified, there's another coordinate that remains hard even after you've conditioned on winning in this first coordinate. And you can keep doing this, just as you go along, condition on all the coordinates that you've enumerated so far. And if you show that all of these, that at each step, your conditional win probability in your next coordinate is 1 minus epsilon, then just a chain rule of will give you that the probability of winning in all the coordinates is at most 1 minus epsilon to the k. So if you can instantiate the strategy with large enough k, then you get an exponential decay bound. The problem, of course, is trying to analyze these tricky conditional probability distributions. So the event that you're conditioning on here could be extremely complicated because the event of winning in some set of coordinates depends on the strategy that your players are trying to use, and you're trying to consider all possible strategies. So this is tricky. And so usually at the core of a parallel repetition theorem is some claim like for all events, there exists some coordinate such that when you condition on the event, there's still a coordinate that's hard to win. And I've redacted a little bit about the claim because as written, this is absurd. If you there are some events you can come up with that just say, like, specify exactly what all the queries are to every player, and then it's easy to win if you know what all the queries are. So usually we'll say if it's for an event that happens with large enough probability, a big enough event. All right, so this is what we're trying to prove. And sometimes I'll say that this is another way of saying this is just that the event E is hard in the coordinate I. And so the approach that we take in this paper is sort of a three-step proof technique. So first we'll show it we'll prove it in a limited case. We'll prove that affine subspaces are hard. So if that's a very special type of event, certainly not all sets are affine subspaces, but first that's where we'll start. Then the natural next step to try is to take an arbitrary event and somehow decompose it and write it in terms of affine subspaces. Unfortunately, this is impossible in general. If you imagine an event just being a bunch of random points, you won't be able to write this as a union of a small number of linear subspaces. So that's not what we do. Instead, what we do is we try to write an arbitrary event as consisting of sort of approximately affine subspaces, as with components that are approximately affine subspaces. So if you go back to the example that I just said about like a kind of an event that consists of just like randomly chosen points, there's some sense in which this event would just look like the entire space. Anyways, after we've done this, we still need to prove that our approximately affine events are hard. And turns out this is the technical meat of our result. And so that's where I'll focus. And since I'm gonna skip sort of the first two steps, what I'm gonna try to give you a flavor of today is that is just like a kind of reduction. That if you have an approximately affine event, which I'll define next, then it's like approximately, it looks like some other actually affine space, and it's as hard as that affine space. Okay, so what does it mean? How can we say that an event is approximately affine? Well, there's like two competing objectives that we want for our definition. And the first thing that we want is that if you have some, say, v tilde, which is approximately like an affine subspace V, then like v tilde and V should be comparably hard. So that means that if you have a strategy that works well on condition on v tilde, then it should also work well conditioned on V, or something like that. The other thing that we want, which I hinted at in the previous slide, was that we need to be able to decompose an arbitrary event in terms of approximately affine subspaces. So these are two different constraints on one notion of what it means for something to be an approximately affine subspace. And the sort of compromise definition that turns out to be okay for both objectives is to say that v tilde is approximately like an affine subspace V if it's not distinguishable by a restricted class of functions, so specifically linear functions over F2. And this is actually a standard notion from pseudorandomness, and it's like a standard notion, and it's called small bias sets, or like v tilde is a small bias in V. Okay. So there's again, I'm gonna just zoom in on just like one little part of this. Showing the general decomposition is sort of less interesting. And the hard part is showing that with this definition of what it means of a v tilde being approximately affine, that it actually captures the sort of values being this, or it actually captures like these sort of being equivalently hard. Okay. So these definitions look kind of innocuous. Like they both look pretty generic, but unfortunately, to actually prove that this notion of approximate affineness is good enough for our objective, we need to use special properties about the game that we're analyzing. It's sort of unfortunate. So special properties that we use for the GHZ game are, first of all, that the query distribution for the GHZ game is uniform over a linear space. So like in particular, the consequence of this that we need to use is that when you look at the parallel repetition of the GHZ game, the query distribution for the parallel repeated game it's actually a tensor product. So this so what you're looking at is like tuples, or three tuples, where each component of the tuple is in f2 to the n, and the triple is chosen uniformly at random, such that the sum of the three components is equal to 0. Okay, so that's sort of the algebraic structure of the GHZ game that we use. And also, so I'm sorry, there's a lot of stuff that I'm just kind of asserting and not proving, because it's just a lot to this result. But so we use actually the fact that for the GHZ distribution, or for the parallel repeated distribution, or for actually anything in between, if you have any strategy, where a strategy means like something that for the player 1 to do, something for player 2 to do, and something for player 3 to do, it's like a product function. Any strategy will either produce independent outputs when you sample its input uniformly at random from this tensor, or all of the each player's strategy has to be somewhat close to linear. So like intuitively, the GHZ distribution has some correlations in it. Like the players are not getting independent inputs. The relation between their inputs is a linear constraint that they sum to 0. And the only way you can preserve this this correlation, or you can preserve some correlation in the outputs when you apply a function separately to each player's input, is by applying another linear function. So that's it's like a little intuitive, but the way to prove it is with Fourier analysis, which I'm going to skip. So anyways, these are basically the special properties of the GHZ distribution that I'm using. So now I can get back to what was like sort of the core claim, which is that small bias sets, or if you have a v tilde that's small bias in V, then v tilde is as hard as V. So yet again, I'm going to focus in on just a specific example of this.
Okay, sorry for interruption. There is a question from Suhail, and I guess it's reference to the previous slide. And the question is Q any large affine subspace?
So can you repeat the question? Is
Q any large? I think this Q, I think it's right. It's this Q from the dichotomy, and so is it any large affine subspace? So that's the question.
Sorry, I'm not. So W is any large subspace, I think, and so yeah, I'm not. there's like two Qs in this. I think yeah. So in the dichotomy statement, it's that if W is any linear subspace, and you consider this tensor of the GHZ query subspace with W, then the dichotomy, I guess, lemma is as stated. Okay. So here I'm just going to focus on the case where V tilde is, yes, it looks like an affine subspace, but in particular, it just is small bias in the entire set of like the parallel repeated query distribution. So here's what that means. And yeah, let's just start with this picture. So on the left, you have your V tilde, which is some small bias set. And on the right, you just have the parallel repeated query distribution, like just represented as a square. And I'm trying to show that when you sample your queries uniformly at random from this funny looking set, all we know about it is that it's small bias, that it's as hard to win in any coordinate as it is in the parallel repeated distribution with no conditioning. So again, I'll just be sketching and hoping to give a flavor of how the result looks. But so first we'll just start by fixing some strategy and some coordinate. That's what we're going to look at, and we're going to try to prove that if this strategy is successful in V tilde with some probability, then there is another strategy on V that works with about the same probability. So given this strategy, we'll build a partition of the whole space. So we'll so each little square in this grid will be a different coset of some fixed tensor. So it's QGHZ tensor W, and this partition is going to have two properties, and it's the first property is that, well, the goal of this whole proof strategy is to kind of take a coarse-grained view of the small bias set and just look at which coset we're in. So we'll set things up so that, first of all, the event that we care about, which is whether or not you win in a particular coordinate, only depends on what coset you're in, and also the output of the strategy in that coordinate. So that's the first thing. That kind of means we just have to look at which coset we're in. But that's like one thing to make sure that we only need to look at what coset we're in. And the second thing is that this strategy that we fixed, when we condition on being in any particular coset, or like an average coset at least, and if we just look at the output of this strategy, so we have a random input within some particular coset, and we look at the output of the strategy, there's the output of player 1, the output of player 2, and the output of player 3. And this partition should have the property that these outputs look independent. So this is not really necessarily obvious, and actually it's quite involved how to construct a partition like this. But it's related to this dichotomy thing that I said earlier, where either they're independent or either the strategy has independent outputs, or each player's strategy is correlated with the linear function. And if it's correlated with the linear function, then you can sort of subdivide your partition and make progress. And then there's some more work to do.
2 more minutes.
All right. Yeah, I'm almost done. So there's some more work to do in going between V and V tilde. But that's the idea. That's where we're using the Fourier analysis machinery. Once we know that the outputs of F on an individual coset are just look like independent, or they're independent outputs, we can use these outputs to define a strategy on V. So each coset has some output distribution associated with it. And the strategy is just look at what coset you're in, and then each player independently like flips a coin to decide his output with the right probability for that coset. And so the last thing that we need to check to see that these strategies actually work, the new strategy we've constructed on V works as well as the strategy we constructed on V tilde, is to say that the coset distribution is the same when we sample in V tilde versus in V. And that's guaranteed by the small bias property. All right, so I'm almost out of time, but just to kind of summarize. So we're trying to analyze this parallel repeated game conditioned on just like an arbitrary event. And we first start with a special case that when the event is affine. And I didn't talk about that, but that uses the fact that the GHZ Fourier distribution is linear. And now there's a way in the paper that we show to write an arbitrary event in terms of affine subspaces that are, in terms of small bias sets. And finally, we show that these small bias sets are as hard as an actual affine space, and that uses some Fourier analytic stuff. And that's all I talked about in this talk, and it was very rushed anyways. So thank you very much for bearing with me.
Okay, thank you, Justin, for your very interesting talk. Okay, so please ask questions, but so far we have one question from René Auerstocher. So, do your method in crucial way depend on the fact that you have 3 players in this case, or can you generalize it to more players? Okay, thank you.
So we didn't prove, or we didn't like write anything about more than 3 players, but I don't see any crucial reason why the techniques here are limited to 3 players. Yeah, like you can easily define a sort of a generalized K-player GHZ distribution. I don't see what would go wrong if you tried to use the exact same techniques to analyze that.
Okay, and you will get kind of the same estimates.
Yeah, it would probably be like inverse polynomial, instead of exponential.
Okay, okay, so we're waiting for more questions to come in. We have a couple of more minutes, so please ask questions. Okay, before we switch to the next speaker.